Good morning, good afternoon, and good evening, everyone. Thank you for joining us today, and welcome to the DAS RCN Community Forum on Global DAS Day. I'm Casey Adderhold from Earthscope. Earthscope is committed to fostering the exchange of scientific ideas by providing a safe, productive, and welcoming environment. All participants are expected to abide by the Earthscope Meeting Code of Conduct, which is in the chat there. This forum will be recorded and archived on the IRIS Earthquake Science Presentations webinar YouTube channel until we have an Earthscope one. So we'll start with some short presentations and then have time at the end for Q&A, discussion, and additional announcements if there are any. Should you have a comment or question, please type into the chat to be read aloud or raise your hand if you would like to be unmuted. In this case, we're in meeting mode, so you can do that yourself, but good to raise your hand. If the meeting happens to crash due to Zoom or internet issues, we will reboot it. Just click the link again. And automatic captions should be available to be turned on and off on your Zoom control panel. So at this point, I'll go ahead and hand this over to Andreas after I bring up the slides here. You should be able to see that there. So Andreas, do you want to go ahead and get us started?
Yes, thanks, Casey, and welcome everybody for the Global Dust Day, I guess. This is just a middle of the month recap of what we have so far and get everybody together and collect a bit of feedback and distribute more ideas. Next slide, please. So, yes, as you all know, in the beginning, I had this little questionnaire, which many of you filled in, and we have quite a good representation over the globe, mostly, no surprise, in Europe and the US, but also a few contributors from the eastern part of this world in this map, so Japan and Australia and New Zealand. So I think this is a good coverage. This map is by no means representative. People should only indicate if they intend to participate. Participation is open for everybody at all time. Basically upload the data to the PubDAS folder as described on the website. But this is still a good overview. So you can see here that most participants are going to be, in all likelihood, academic institutes, a few commercial interests, participants, and people who identified themselves as other, or organizations who identified themselves as other. And most of the cables will be, probably also no surprise, shallow buried. And interestingly, like a good list of potential installations, but interestingly also we have quite a good number of other installations. So that will also be interesting, what identifies as others. I think Herb has an underground mine there. So I guess that classifies as others. So I guess we get a good coverage of various data sets. So it will be very interesting. Next slide, please. Yes, as I said, most contributions are also from Europe here, a bit from the US, and contributions also a good mix of certain and tentative. No other here, and a good mix of cable length here as well, anything between, I guess, 400 meters and 90 kilometers. So this is only indicative of what we have. We will ultimately see what the contributions will be. Next slide, please. So as of this morning, we had 81 earthquakes with magnitude 5 so far, including 2 rather tragic ones in Turkey And actually, there's a lot of aftershocks happening there as well in the zone, as you all probably know. So 81 earthquakes in half a month. I think this, from a data point of view, this is a good overview. And having the big Turkey earthquake is, of course, as always in earthquake science, it's always tragic to have this earthquake, but it means also that we have an interesting data to work with, and hopefully we can maybe use this data to also understand the whole mechanics of that area a bit better. Next slide, please. Yes, again, just a reminder of what the specifications were. We record during this month, obviously. The license is, I call it here Creative Commons, basically just to indicate that the data will be completely public, as is, I guess, common practice with seismological data. We wanted also to find out how would commercial data owners, let's say, react to such a concept, so we can work as a community towards getting access to such data sets that are commercially acquired, to make it more probable that these data will be available. We asked for downsampled data, both possibly in time and space. And to make it simpler, to use the native interrogator format. But if some downsampling is needed, it turns out that some units is difficult to get the downsampled data out. So that's already something interesting. If you share the data, also some support files should be included. So readme.txt with just free-form text description of the data, the site, the cable, contact information, and so forth. If you go to the web page, I guess I will put that in the chat later. So on the NORSAR web page, if you click on those, basically all that information is on that post there on the NORSAR web page, and there are example files, each of them, so you can have a look of what I had in mind with these things. So if you don't have already done that, this could be used as a guideline maybe. So also the metadata should be included, obviously the coordinates. Thanks, Casey, for sharing the link. And then obviously also a reader in any format, so that people can also read your data format that you share the data with. And maybe that also helps to with everybody's toolboxes that they probably have internally to work with data, that they can expand that to hopefully all possible data formats out there. This will then also help for identifying with the IRIS RCN working group data format. So hopefully these different readers will then feed into the discussions. What are the best ideas from each data format out there available? So this is actually will hopefully be very helpful for everybody. So the data should be 100 Hertz DAS data convertible to strain or strain rate. So if you have it in radians per square root of Hertz or whatever is your unit, then your reader should be able to transform that into strain or strain rate. So whatever is your native data format, but your reader should convert it into strain or strain rate. The 100 Hertz is not strict. So if you have, for some reason, it's easier for you to have 110 Hertz, or whatever data format that is makes it more easy or more efficient. Even 50 hertz, I guess, or 60 hertz. Just having 1,000 hertz is probably too much for the data repository and also for people to download them. Spatial sampling also about 20 meters. Again, if you have 24 meters or 18.6, that is also very much acceptable. And then we have triggered data also to keep the data or the storage manageable. We have 1 hour per event, starting from the origin time of as defined on the USGS website. Next slide, please. Yes, and as of today, as you probably all know, we have today a continuous day. So starting with midnight UTC to midnight UTC today, we encourage people to store continuous data for research on that, basically noise or other work, what's the fundamental mode data. So we actually have then this data available for research. So we basically share 24 hours, and that can then also be downsampled more to 500 hertz, but 50 hertz, sorry. But that also depends on your overall data load. Don't just be reasonable and think that people have to download the data to actually work with it. Yeah, and next slide and last slide. I guess lessons learned so far. So this is mainly for me to share this kind of thoughts with you, with the community. I'm still very pleased and happy, and yeah, it's very interesting to hear that there's an immense interest in the community. I think Casey said that today on this call we are 75 people. So just to give you a sense, there's quite a good amount of people here. There seem to be difficulties, more difficulties than originally anticipated to secure permissions from commercial data owners. So that's an interesting thing that needs to be picked up by the community for the next efforts, I guess, in this thing. This has been more challenging than I originally thought to organize that as a grassroots effort. Well, as you can imagine, there are many opinions on what is best. So, and I think there is, there was a lot of learning there as well. And this is still interesting and still fun. And how do we go with this learning forward? I guess that remains to be seen. But I think a more organized way with going forward with IRIS, EarthScope, or Orpheus on the European side, that I think this is for us to decide in the next, once we have the data collected. Another challenge is then also the data format. You may remember that there was the effort for a unified data format, and we then moved on for a heterogeneous data format, so using the native data formats. Everything has its pros and cons. So that also remains to be seen for the future. That was to be expected to be a critical point, and so this discussion is probably very useful for the way forward that we had. And then also something that surprised me, that downsampling is surprisingly often a challenge, not only because of the hardware challenges involved, but also workflows and allocated times in certain organizations. You always need people and capacity to do the actual work, and that is often not there. So there's interest in some organizations to participate, but sharing the data then in the non-native recording structure is a challenge, and that also needs to be addressed if we are going to share kind of data with commercial operations. So, and that's from me here, and I'm happy to hear now the different contributors. And maybe also what they have to say to these points.
All right, thank you. So I think we'll start off here with Kit Chambers in just a sec. Gotta get the slides up for that.
Yeah, are you going to share or should I?
Yeah, I can. Yeah, sorry, I'm
Okay.
getting that right now. Go to. Okay, is that the first one?
Yep, yeah. There's only 2 slides. It's not
Did it
not
just
too
back?
extensive.
Sorry. Okay.
Okay, I guess this is the sort of data set that we recorded, and I'm not really sure how it fits into the Global DAS Month. I actually know very little about the Global DAS Month on that front, but I thought people on this call might be interested in it anyway, and it might foster a little bit of discussion about how to best collaborate with industry partners in this group, if nothing else. So essentially, my company, Motion Signal Technologies, does a lot of work with Focus Sensors Limited, who make a, what is it, phase coherent interrogator, I think that's the right term. And they are doing monitoring along a large section of train line up in the Midlands, UK. And so there's 2 lines sort of shown on the sort of map there, that those are sort of extending north from the city of Leicester. There's actually 3 interrogators in that section, because the fibers take a bit of a weird path in there. And as part of that, we're trialing a data compression and transmission system, which MST is bringing together. And so when the earthquakes happened on the 6th of February, we went and had a look to see if we could see them, and lo and behold, we can actually see some quite clear signals from these earthquakes in the data set. We thought that, and so the thinking is that, you know, we don't have enough time in order to look at these things. For me, global seismology is an interesting thing, but a past life. So what it really needs is a non-commercial or academic organization to go and have a look through it, because it's a pretty extensive data set. You're looking at there's 1 meter channel spacing with sensors spread over about 30 kilometers. There's about 45,000 channels in total on this data. Even after it's been downsampled, it's reasonably challenging to work with. So if you could flick on to the next slide. This is on the right hand side here. You've got a section of data that's about an hour and a half or so, filtered for the surface waves from the event in eastern Turkey, and you can see quite a lot of sort of quite clear things in there. So you can't see my pointer, but you can see the way arrivals change in amplitude as the fiber changes direction. Presumably, somebody who knows a lot about surface waves could probably pick out a lot more detail in these types of events than we could. And we have a full 24 hours of data, so there would be data for the second event that happened at about 10:30 that day as well, or for that matter, any aftershocks. As I mentioned, this is a commercial data set, so so in terms of there's some sticking points with regard to sort of general release. The Creative Commons license that is being used for PubDAS is something that's a little bit, will make companies a bit nervous, or at least some companies a bit nervous. I guess they can make their own decisions on this front. There's a risk of somebody taking your data and giving it off to someone else, or and that data being used in some way to sort of harm your business. So we want to. So for the moment, we're saying that we're happy to release this data to academic and non-commercial institutions, but we can't just give it to anybody at this point. In terms of getting hold of it, there's the CATE, compression and transmission system, that MST uses, actually has a web interface which allows you to download all, some, or none of the data from the array, and it's a sort of fairly simple sort of set of instructions. There's standard things available in Python as well as other languages. That's kind of where we're at on this, on the sort of first talk. So I don't really know what everybody else is going to say after me on this. But you know, I'm happy if people want to ask me questions about this data, either on here or afterwards. I'll be happy to help out in any way I can.
Yeah, thanks, Kit. I think it was important here to have you as well contributing, and just also hear somebody who is actually not submitting the data to the global dust month. So also to show to the community what we may be missing. I mean, you still say that it might be available. So, but I think
we want people to work with this data. I mean, it's, you know, nobody wants to sort of stifle scientific research. What you don't want to do is shoot yourself in the foot at the same time.
And the question with the Creative Commons, that was only me as a layman deciding for going for Creative Commons. I guess that's again the organization that then takes over this data sharing should have some people that are more familiar with the different licensing types and get feedback on that, what is actually be doable and what that all implies. So thanks for your feedback.
Happy to be a part of it. So there is a question.
Oh, is there? Oh, sorry. I can read that out. So from Les Garcia. Hi, sorry, Kit, could you provide info about the band of frequencies of signal you show?
So the data's sampled at 62.5 hertz, so it's sort of good up to about 30. In that plot, I think the data was filtered for sub 10 seconds. So there's one of the good things about the Indus systems is it's got quite good low frequency sensitivity. So I found that just looking at the data that, you know, if you went sort of more than that, you didn't see the surface waves as well. I was looking to make a pretty picture, really.
Great. All right, I think we'll move on to Daniel. So let's get your slides up here real quick.
Hi, yeah, thanks, Casey. Our group is running a project in Istanbul. I'll show a more zoomed out picture at the next slide, but this is a collaboration between ETH, our colleagues at the university in Turkey at Kandili Observatory, also April Bozdag at Colorado School of Mines. And the project is using dark fiber from the municipality of the city. The city operates these fibers, and I have a long list of names that aren't on here of people who helped us get the dark fiber access. Next slide. So it's this purple line kind of to the bottom right. We're planned to do 30 kilometers. It was only 8 kilometers for the first half of the month because we had to repair a fiber link. The engineer who was supposed to do it for us in the first week was sent to go help the earthquake zone. So I can't complain about that. The DAS line runs along the coastline here by the Princess Islands, and it's supposed to be close to the Anatolian fault zone. Next slide. And this is the last slide. Of course, we recorded the strong signals from the 7.8 and many of the aftershocks. This particular figure was from a master's student, Ali, who was there and doing the initial looking at the data. Of course, there'll be a lot to dig through and a lot of people smarter than me to analyze this and tease apart information from these.
Can you say something about the sampling rate?
Yes. So our native sampling rate is 200 hertz, but we'll be able to download it, downsample it, of course. We're using 8-meter channel spacing. I don't know if I can get that to then exactly 10 or I think it was exactly 20-meter channel spacing, but we'll get something close to that. Yeah. Should be fine. I do want to mention there are two other ETH projects ongoing separate from this Istanbul project. One is by a colleague who's measuring signals along a river here in Zurich. That's a Phoebus interrogator being operated by Pascal Edme. And another is from Tjeerd, actually online. Tjeerd is a student also at ETH who's running a project looking at landslides in the Alps here in Switzerland. So he has, I think, 6.5 kilometers of trenched fiber. It only started running a couple days ago, but Tjeerd will still upload what he can.
And did you have any difficulties or kind of the discussions inside ETH to participate in the Global Dust Month? Any feedback on that?
No, I think it's a great initiative, and separately from all of this, we have a small grant specifically to help look at DAS data formats and sharing and making things open source. So I want to help with all of this, and the fact that we can make this Turkey earthquake data open is great from my point of view. We are using, I didn't mention this, we are using a Silixa interrogator. I guess there's some folks from Silixa on as well. We were told that we shouldn't necessarily share the raw Silixa data because there's some header information that has things like serial numbers in there. But we have a very simple script that'll basically take out the headers we don't want and keep the headers we do want, and make everything good with the iris list of what's needed.
There's a comment, Daniel, in the upper graph is averaged over length.
Sorry that I took off the label. That's just one example trace. Ali just picked out one single trace just to kind of show how a single one looks. And this is over a very broad band. This is 1 to 100 seconds. Yeah.
Great, thanks so much. I think we'll move on, but if you have any other questions, you can continue discussion in the chat there or follow up afterwards. So I think next we'll have Lena. You'll be sharing?
Yeah, I will share my screen. One moment.
No worries, you're good.
Yes.
We see it. We're good. Thank you.
Yes. So good day, good afternoon, good morning, everyone. Today, me and my colleague Daniel, we prepared a few slides to introduce the company Epicensing we work for, because I believe in this seismic community. Maybe you don't use quite often our interrogators, so probably you don't know us a lot. So we are manufacturer of DTS and DAS interrogators. Our headquarters are based in southern Germany. Here you see in the center of map. But we are a global organization. We have several offices all over the world. So we have a long history of measurements. Initially, we started as a DTS company, but now we are also, of course, developing our DAS interrogators. And within each of these kind of units, DTS and DAS, we offer different variants, different measurement range, different channels, different performance characteristics. And of course, we offer configuration tools and analysis tools, our software. And since it was suggested to show and to tell why do we love DAS, I couldn't skip slide like this. I want to tell that we really love DAS at AP Sensing. And with the DAS, we involved in different areas, monitoring areas, different applications. And with our DAS, we are involved in power cable monitorings, pipeline monitoring, rail monitoring, different application in oil and gas, different geotechnical applications, and we can do very different things, amazing things with the DAS, with the data that we acquire from DAS. It's a power cable fault location, TPY prevention, peak tracking, leakage detection, railway monitoring, track monitoring. Also, we know how to work with this big data. We apply different machine learning techniques. And so this extensive experience in absolutely different areas, access to the worldwide monitoring assets, desire an opportunity to contribute to this amazing campaign, DAS monitoring campaign. So were the major factors that we are here. And of course, we have something to introduce to the seismic community, let's say. We have DAS that can measure up to 100 kilometers. Our DAS can provide outstanding signal to noise ratio at low frequencies, long ranges. And of course, it's just amazing that you can connect DAS to the standard telecommunication fiber and get good data for further researches. Yeah, so this slide is our, let's say, main installation with which we are participating in DAS campaign. It's a rail track in Switzerland. The length of this track around 50 kilometers. The initial acquisition parameters, it's a spatial sampling 5 meter and repetition frequency 1 kilohertz. We have not yet created the folder for our data on the PubDAS because we need to kind of align the data, our data that we have from our DAS and from our asset aligned in terms of what it has to be done to upload to the PubDAS data. It takes us some time. But the interesting thing that first, it's a quite long asset, as I said, around 50 kilometers. And it's not just a straight line. So it's kind of L-shaped track. So it means that you can have at least 2 directions, let's say, of measurements at the same time. So I guess it can help more to define different directions of whatever seismic waves. Yeah, and besides of this data, we have other data that we can potentially share with the with you, with the research society, but I'm not sure that we are able to upload everything on the PubDAS folder, and probably will not have all the permissions. But if you have interested in your institute's organization, please let us know, contact us. We are always happy to help and share maybe data directly with you. And I have so we can share some data with some power cable objects that also sometimes in perpendicular to each other, that also can be of interest. And also I probably heard several times that there is some problems in terms of knowledge sharing between industry and academia. So if you have any questions about the DAS DTS systems itself, you always can write us and ask any questions you want. We always happy to share our knowledge. So here are some contacts how you can reach us. Thank you very much. I think, yeah. Can I stop sharing?
Thank you.
Thanks, Lena. Very interesting data set, and thanks for participating as well.
Thank you for this amazing campaign and organizing.
Right, I think I'll then go ahead and move on to our next presentation, but feel free to put some questions in the chat. So our next one will be Fabian, and I've got a video to play. So this should hopefully work.
Hi, I'm Fabian and I'm a postdoc at LMU Munich. And here we're today at the Schneefernerhaus, which is the highest observatory in Germany. We set up an IDAS here, which is a device to do distributed acoustic sensing along a fiber optic cable, which is placed here in a tunnel that goes beneath the ridge of Mount Zugspitze. The aim here is to do permafrost research, as this ridge actually crosses a permafrost body. So the cable that we're using for distributed acoustic sensing is a bit more than 1 kilometer long. To find the position of the cable, we do some tap tests. That is, we go along the tunnel, and wherever we have coordinates, we tap to the cable and connect this cable segment to these locations or GPS coordinates that we are standing at. Yeah, I can just add a few more words. I took this video from a previously recorded video, which was done by my colleagues from ETH Zurich, and I thought it might be nice to show just a few pictures on the cable location and so on. Yeah, so the interrogator is running at the moment. We don't have remote access, but I got confirmation from the site that it's still running. As said in the video, it's about 1 kilometer long with 2 meters spatial sampling at the moment. And I think we don't have any data gaps so far. So I think we can upload all the data basically that we have available. Yeah, thanks.
Thank you. Points for a lot of beautiful video clips there. Any questions from the audience? Great. And we can always get some more questions later, but I think we'll, in the interest of time, we'll move along here now to Agatha Podrasky. Would you like to go ahead and unmute and share your screen?
Thanks, Casey. Can you see my screen now?
Yes. And if you go into presentation mode.
Yes.
Perfect. Looks great.
All right, great. Thanks, Casey. So really quickly, I'm going to just share about the detection of the turkey teleseisms from our location where we're participating in the DAS Global Field Campaign from Fairfield, Montana. So I'm going to start just by introducing our installation we're using and the instrument, and then I'm going to hand it over to senior geophysicist David. We'll talk about some of his preliminary data analysis. So we're measuring from Fairfield, Montana, all the way across the Atlantic in the northwestern United States. And the town of Fairfield is a small rural community in the northwestern part of the state, but just on the other side of the Rocky Mountains. And there we're measuring on a 28.4 kilometer dark telecom fiber, just directly buried, running west from the small town of Fairfield through agricultural lands toward another small town of Augusta, Montana. And we're remotely operating the instrument from our office, Silixa's Environmental and Infrastructure North America office in Missoula, Montana, about 144 miles west of Fairfield. So we're operating an IDAS MG, which is Silixa's multi-gauge length IDAS. And the current configuration we're using is 400 Hertz sampling, so detecting signals up to 200 Hertz. And then, of course, for the DAS campaign, we'll be downsampling that to deliver the data at the specified sampling frequency for the collect. We currently have a 4-meter sampling interval and a 30-meter gauge length. And then I'm going to hand it over to David to talk about some of the preliminary results of detecting the turkey teleseisms.
Yeah, thank you. So this is just a really quick first look at this sort of unfortunate opportunistic event or that occurred in Turkey and northern Syria earlier this month. So what we're looking at here on the right is a stack of traces along the far end of the cable from about 24 to 26 kilometers distance. And I'm not a seismologist, but I think what we're seeing based on the travel times is a P and then maybe an S or a P to S later at about 0143 or so. And so the signal to noise is surprisingly good for such a far event. And of course, this is just an opportunistic dark fiber install. So some of the issues that we contend with on these types of campaigns, dark fiber campaigns, are like coupling quality of the cable or cable types or optical losses, things like that. I will say that one of the real positive aspects of recording at a telecom company is that they have really, really fantastic upload speeds because they're an internet service provider. So we should be able to get these uploaded maybe just directly from Three Rivers, although that might be an asking forgiveness rather than permission kind of thing. But yeah, that is one interesting aspect. So in this part of rural Montana, it's pretty rare to have such good internet. Yeah, I think next steps are to look at whether we can see any aftershocks or the secondary large event, and then follow on with the full catalog provided by Andreas from USGS. Can you go to the next slide, Agatha? So here's that first P arrival along the whole cable in a wave field view, and then we can also see some highway traffic, these sort of slowly sloping lines transecting the wave field as well. We tried to get rid of some of that, but haven't tried too hard. We haven't done any sort of slowness filtering or anything like that, but this is installed along the traffic highway, so we see some trucks and cars and things like that. And then can you go one more slide, please? And we'll look at the P to S or the S arrivals. So here we're looking at both of these plots filtered from 0.1 to 10 Hertz. So there's obviously some opportunity maybe to look at some different bands or do some more filtering to get better results. But I think this just shows, combined with all of the other really nice results we've seen so far today, the feasibility for using DAS products even opportunistically for adding to the teleseismic monitoring that's already being done. And that's all we had to share for today. So thanks for allowing us to participate and share with you.
Yeah, thanks so much. And our email addresses are here if you have any questions, and we will be sharing all of the data for the entire month.
Maybe I can ask either one of you, Agatha or David, what is Silixa's experience or take on the kind of licensing problem that was discussed earlier? Did you have difficulty securing a data set of the many you're working on?
So this is a Silixa deployment. So we have a partnership with Three Rivers Communication for the dark fiber access. So all of this data is being collected internally from Silixa. So the decision is really up to us to share it. We work on so many client projects and we aren't able to share any of that data. So this is an exciting opportunity for us to get to collect the data ourselves and share it directly with the community.
All right. Thank you so much for participating. I don't see any other questions, so I'm going to move us along because we've got 2 more presentations and we'll have a couple minutes at the end for questions. But our next one is another pre-recorded video. So I'll go ahead and share that now.
today. Apologies that I can't be there in person, but hopefully what I can do is give you a flavour of what our deployment looks like. So it's a pleasure to be here, and I'll introduce myself. My name is Andy Nowacki. I'm at the University of Leeds, and alongside colleagues and others, we have deployed our interrogator at the Eskdalemuir seismic array. I should point out that this work is done with my colleagues in Leeds, Sjoerd de Ridder and Adam Booth, and close collaboration with David Green at Blacknest, which is part of the UK's atomic weapons establishment, who provided much of the funding. Also like to give thanks to Gaëtan Calpry of Phoebus, who have supplied our instrument, which we bought off them, but also trained us in the use of it and helped us with the deployment a great deal. And finally, thanks to Stuart and Gareth, who work at Guralp, who run the Eskdalemuir seismic array. Here is a picture of that array. It's one of the Comprehensive Test Ban Treaty Organisation's international monitoring system arrays. And so it's the UK's contribution to monitoring for explosions that occur around the Earth. It's a seismic array made up of a number of broadband and short period instruments located where the triangles are, and so you have an array which has an aperture of about 10 kilometres with these two arms. Now what we've done is we've used the fact that there are fibre optic cables which connect all of the stations in the array together back to the seismic station, and we've attached our interrogator, which is a Phoebus A1 unit, to the end, and use that as our sensor. So the cable runs out of the seismic station to an intersection hut here, and then up to the station at the end along this so-called blue arm of the array. Now this is a fibre which has a bundle of multiple fibres, and so what we've actually done is we've connected the ends up at the top of this arm here, so that then the light runs back down the fibre in the opposite direction in a different fibre in the same bundle, I should say, back down to the intersection hut, and then back out along this so-called red arm of the array, where we've connected it up again in a loop, so it goes back down the bundle, down the cable, and in fact then down towards the southern end of this blue arm. So you'll see that we have this kind of rather unusual thing where if I show just sort of the altitude along the cable, you'll see there's about 200 metres of topography over a total length of about 38 kilometres of cable. There are these points where we have a symmetry in the signal as well as in the topography along the cable. That's a function of the fact that we have connected them up at the end so that we have this long fibre. So if we have a quick look at there's a sort of random snapshot of data, of noise at some point in time. What we can see is that we have signal out to kind of something about 30 kilometres. Beyond that, the losses that we have are a bit too large for us to really use that signal anymore. And here I'm showing nanostrain per second. It's there in terms of strain rate. So you can see there are some sort of quiet sections, and these are where the cable is buried quite deeply. So it's buried inside some ducting down to about kind of a metre below the surface. In some sections it's at or near the surface, and that's where we have more noise. There are also sections where it's underneath streams, or actually, as you'll see, sections where it's just flapping around in the air. So we have some noise from lots of local effects happening there. You can see quite nicely in the data the symmetry points where the cable reaches the end of the fibre is at the end, and we've connected it together in a loop. You can see that in the symmetry and the noise that's just in this data here. And so finally, just some pictures from the field work. This is sort of a rural part of Scotland. It was chosen to be relatively quiet in terms of noise for its monitoring purposes, but you'll see that our cable, as here, does have places where it is susceptible to, shall we say, to wind and noise and other sources. At the same time, we've deployed a set of seismic nodes along the cable because the array itself is mainly one component, vertical component. Our fibre is laid horizontally, so we put some 3-component nodes out as well to give us some extra information. Okay, that's a quick rundown of our Eskdalemuir deployment. Be very happy to liaise with questions. If you have any, please do send them over Thank you for your attention, and goodbye.
All right, thanks so much. So I did note that Andy's contact information is in the chat there. So if you do have any questions, you can direct those to him directly. So I think we'll go ahead and move forward with our last presentation that I know of, at least, which is Alan Baird. And I'm going to go ahead and share your slides here.
Hi, thank you. I'm here to present NORSAR's contribution to the event. At NORSAR, we have recently developed our own new fiber optic experimental array, which is actually co-located with the with our seismic array NORES, and we call it NORFOX. It consists of about five fiber arms that arranged in sort of this star-like pattern from the center, covering an area of around 3 kilometers diameter. And each of these arms are looped up at the end, spliced at the end, so that we can connect to any arm and then add additional arms in sequence. And this adds some resilience and means that if we have a cable break somewhere, we can easily remove one arm and still acquire valid data. The cables are buried around 5 centimeters depth, and we have 2 cables buried, an OFS cable with 2 enhanced fibers and 2 telecom fibers, and a hexatronic telecom with 4 fibers in it. In addition to that, we installed 2 empty cable pipes for possible expansion in the future. And you may notice that in the plot here that not all of these arms are smooth, and there's some of these strange departures from the main trend. And there's a reason for that, which you can see in the next slide. Next slide. Yes, and basically the terrain is not cooperative everywhere, and sometimes you end up with these hills that we need to, for practical purposes, deviate from the main trend, and that's the reason for those. I'm just going to show you some pictures of construction in the next slide. Yeah, so this is the digging and the cable laying. And I believe the construction started at the end of September and is actually still ongoing. It's almost finished now, but it wasn't entirely complete for this month. But we do have several arms that we're interrogating on. Next slide. And this is just showcasing some of the challenging environmental conditions that our colleagues have to work with when splicing fibers in the Norwegian winter. But they're making progress, and we're gathering some good data now. Then next slide. This is just an overview of the acquisition settings. We actually have 2 interrogators that are connected at the moment. The first is the ASN Optidas, which is recording at 100 hertz sampling rate with 20-meter gauge and 10-meter channel spacing. And that gives us an hour of data, gives us about 1.3 gigabytes. And then in addition to that, we have a Phoebus A1R, which is also recording at 100 hertz with 20-meter gauge spacing, but slightly tighter channel spacing. And this gives us around 3.9 gigabytes. And at the start of the month was actually the first time we ever connected interrogators to the system. And at that time, we only had 3 arms that were completed. And we actually had a problem with arm A. There was a break in the link at the end, which means that we can only we can't actually record the return on the A. So we connected the cables through arms C, B, and A. And in the next slide, I'll show you some examples from the Turkish earthquake. Okay, so these are data recorded on the 2 interrogators. The data are initially recorded in strain rate for both interrogators, but we've converted to strain for this example because it better showcases the earthquake, I think. And I filtered these with a bandpass filter of 0.01 to 5 hertz bandpass. And you can see that this is 1 hour of data from the start of the earthquake, and we traverse arm C 2 times because outward and reverse arm B, and then arm A just outwards. And you'll notice that there is some noisy channels, especially in the Phoebus interrogator, and we still need to investigate why this is occurring. We think there may be an issue with the fiber in this, but we need to investigate. But as you can see, we get pretty high quality data on both interrogators for the outgoing portion of arm B. And for that, I pulled out example channels that are approximately co-located between these 2 interrogators, just to show the comparison. They're very quite similar to each other. So we're quite pleased with the results so far. And that's pretty much what I had to present. I should also mention that I've been asked by my colleague Ben Dando to advertise a session that he's convening at the IEGG conference on advances in earthquake and explosion monitoring using DAS. If you want to submit an abstract, I think some of you might be interested in that, given the topic. The deadline for abstract submission is next week.
Great, thank you so much. So unless there's any questions, I think at this time, we don't have a lot of time for discussion, but there have been some questions along the way. Andreas, do you have any comments before we wrap this up?
No, I think that was all very interesting. It was nice to see the different contributions. And I think it's just to remind everybody to check out the PubDAS upload server. Unfortunately, Zach couldn't participate today here. So I think we need to get familiar with uploading data there. And we said that the upload will be open until 31st of March, so 1 month after closing off. So that should give hopefully people enough time. If you need more time, just let me know. We are not 100% strict on that. It would be good to have the data though, because I aim to collect all that and see if we can get a nice publication out. So, and then have all available information of how big the data actually is and what we actually have in the data set. That would be very nice to have that as soon as possible.
Okay then. So I'll go ahead and close this out. So thank you so much to Andreas for organizing this entire effort. You've done great. I know it's grassroots, but I'm pretty sure you're the main root in that. And then also thank you so much to our presenters today, Kit, Daniel, Lena, Fabian, Agatha, David, Andy, and Alan for your presentations today. The recording will be made available on the IRIS Earthquake Science Presentations playlist. If you're interested in future DAS events, please join the DAS mailing list and check out the DAS RCN website. And thanks so much for joining.